Hello students, in the previous lecture we have discussed about the ideal gas equation, right? Okay, now in this class we are going to see about the Graham's law of diffusion. Okay, so before going to this Graham's law of diffusion, first we should know that what is this diffusion. Okay, so what is the diffusion? Is that very simple. The diffusion is a process, that is a property of a gases to spread and occupy the all available space is known as a diffusion. Okay, that is nothing but it is a property of a gas that will, that the gas can spread and occupy the all available space, right? Okay, the example is that fragrance of perfume. Okay, so in a room you take a perfume and you spray it. Okay, what will happen? That fragrance of that spray will take all the portions of that room. Okay, that means it will spread and occupy all the available space, and that kind of phenomena we call it as a diffusion, right? Okay, and there is another property is also there, that is the effusion, right? This is also a property of a gas, effusion. Okay, so what is this effusion? Is that because sometimes you will confuse what is the diffusion and what is the effusion. Okay, so the effusion is nothing but it is also type, but it is an escape of a gas from high pressure region to into the space through a fine hole, right? So escape of a gas from high pressure region into space through a fine hole is called it as a effusion. The best example is that escape of gas from cylinder, right? You know that inside the cylinder there will be a high pressure, and when you open the knob it will start the flow. Okay, escaping, there you call it as a escaping. That is not a diffusion. Okay, it is not going in itself, right? It is forcefully coming out. Okay, so that you can call it as a escaping. Okay, so that phenomenon, that property you call it as a effusion, right? Okay, and you know that come to the diffusion, it is a non-directional phenomena, right? So when you fragrance the perfume, right? When you spray a perfume, what will happen? It takes all the direction, right? So that it is a non-directional phenomenon. And here it is a unidirectional. Unidirection is one direction. Okay, so that means whatever the gas will passes from high pressure to the low pressure, so that it is a unidirectional phenomenon. Okay, and here diffusion, the Graham's law is applicable for both the phenomena. This Graham law is applicable for both the diffusion as well as the effusion, but we are not going to be read the effusions here. We are going to read only the diffusion, right? Okay, right. And next one is that before going to this, again, rate of diffusion. What is the rate? Rate ante enti anante ఎంత టైం లోపల అది ఎంత డిఫ్యూజ్ అవుతుంది, ఒక పర్టికులర్ టైం, ఫర్ ఏ పర్టికులర్ యూనిట్ ఆఫ్ టైం హౌ మచ్ ఏ గ్యాస్ ఈజ్ డిఫ్యూజింగ్. ఓకే, అంటే ఒక పర్టికులర్ టైం లోపల ఆ గ్యాస్ అనేది ఎంత స్ప్రెడ్ అవుతుంది. సో యూ టేక్ ద 2 పర్ఫ్యూమ్స్ అండ్ యూ స్ప్రే. సో ఒక 2 పర్ఫ్యూమ్లు సేమ్ స్పీడ్తో స్ప్రెడ్ అవుతాయా, డిఫరెంట్ స్పీడ్తో స్ప్రెడ్ అవుతాయి. దట్ యూ విల్ క్యాలిక్యులేట్ విత్ ద రేట్. Okay, so what is that rate? The rate is equal to volume of the gas diffused. ఎంత వాల్యూమ్ మరి 1 ml 2 ml ఎంత మనం స్ప్రే చేసాం, డివైడెడ్ బై ద టైమ్ ఆఫ్ డిఫ్యూజన్. ఎంత టైంలో అది డిఫ్యూజ్ అయింది ఒక పర్టికులర్ ప్లేస్ నుంచి ఇంకొక ప్లేస్లోకి. ఓకే, వెరీ సింపుల్. ఇట్ ఈస్ రేట్ ఆఫ్ diffusion. That the volume you call it as a V and the time you call it as a T. So that is R is equal to V by T. R is equal to V by T. Okay, now we can enter into the Graham's law of diffusion. Okay, what is the Graham's law of diffusion? What he found with his experiments is that very simple. At a given temperature and pressure, that means at temperature, pressure అనేది కాన్స్టెంట్ అన్నమాట. ఓకే, ద రేట్ ఆఫ్ డిఫ్యూజన్ ఆఫ్ ఏ పర్టికులర్ గ్యాస్ ఈజ్ ఇన్వర్స్లీ ప్రపోర్షనల్ టు ద స్క్వేర్ రూట్ ఆఫ్ ఇట్స్ డెన్సిటీ. That is R is directly proportional to the 1 by square root of density. That is R directly proportional to the 1 by square root of D. Okay, అంటే ఏంటి అంటే కాన్స్టెంట్ టెంపరేచర్ అండ్ ప్రెషర్ దగ్గర the rate of diffusion of a particular gas, that depends upon its density. Okay, that is is it directly proportional? No, inversely proportional, right? Okay, so that means if the density of a particular gas is more, obviously the rate of diffusion is less. Rate of diffusion అంటే అది చాలా స్లోగా డిఫ్యూజ్ అవుతుంది అన్నమాట. ఒకవేళ డెన్సిటీ అనేది తక్కువ ఉంది అనుకోండి, ద డెన్సిటీ ఈజ్ లెస్, ఆబ్వియస్గా ఏమవుతుంది, డెన్సిటీ అంటే ఏంటి, లైటర్ గ్యాసెస్, తక్కువ వెయిట్ ఉన్న గ్యాసెస్, అవునా కదా, లైటర్ గ్యాసెస్. ఇఫ్ ద డెన్సిటీ ఈజ్ మోర్, హెవియర్ గ్యాసెస్. సో హెవియర్ గ్యాసెస్ స్ప్రెడ్ in a more time. Other lighter gases ఏంటి, easily they can spread. Okay, very simple. Okay, if suppose two gases ఉన్నాయి, there are two gases, right? There are two gases, and ఈ two gases ని తీసుకొని మనం when you spread, okay, so with the for these two gases again the densities are different. So this gas density is d1 and this gas density is d2. Okay, so then when you spread it, so what will be the rates? If this gas rate is R1 and this gas rate is R2, right? So then what is the relation? The relation is that very simple. If R1 and R2 are the rates of diffusions of two gases and D1 and D2 are their densities respectively, then there will be a relation that is R1 by R2 is equal square root of D2 by D1, square root of D2 by D1. How it is? Very simple. You know that R1 is equal to the R1 is equal to directly proportional to 1 by square root of D. Okay, so here it is, I am writing the R1 1 by square root of D1. Okay, similarly R2 square root of D2. Okay, you take the R1 by R2. So here when you take the ratio, you can write directly to the equal, that is 1 by D1 divided by 1 by square root of D2. Okay, so then you can write this as a, right, so that is R1 by R2 is equal, it is a simply mathematical relations, nothing chemistry is there here, right? Okay, square root of D2 by square root of D1. So this you can also write it as a whole square root of D2 by D1, that is R1 by R2, right? Okay, so this is the relation, right? But there is a one more relation, that since the density of any gas is directly proportional to its molar mass, you know that, right? In Avogadro's law we have also seen, that is in the Avogadro's law, just once again I am showing that Avogadro's law, whatever that mass is directly proportional to the density, that means the density of a gas is directly proportional to its molar mass. Okay, so density దేనిపైన డిపెండ్ అయి ఉంటుంది, దాని యొక్క మోలార్ మాస్ పైన డిపెండ్ అయి ఉంటుంది. Okay, so that means m is directly proportional to d, right? So that means instead of d you take the m, molar mass. d ఉన్న దగ్గర m తీసుకోండి అంతే. So that is r is equal to, again 1 by square root of m. So that means again R1 by R2, this is directly proportional. R1 by R2 is equal to again square root of, ikkada D2 by D1 kada, ikkada M2 by M1, M2 by M1. Okay, simple. Again here what is the M1 M2? M1 M2 are the molar masses of the two different gases. Like take example of the hydrogen and helium. Hydrogen molar mass okati, helium molar mass okati. Okay, next there is a one more relation, that is molar mass of a gas is directly proportional to the, again its vapor density. It is vapor density, that means the molar mass again it is directly proportional to its vapor density. Vapor density is Vd. Okay, so generally the m is equal to 2 into Vd, but don't worry about the 2. Okay, so here r is again directly proportional to the 1 by square root of Vd. Very simple, instead of the molar mass you write the Vd, that is R1 by R2 is equal to again square root of Vd2 divided by Vd1, vapor density of the second gas divided by vapor density of the first gas. Okay, very simple. And you take the relations everything in the one format, that is R1 by R2 is equal to square root of D2 by D1, and again is equal to the square root of M2 by M1, and again square root of Vd2 by Vd1, vapor density of the second gas divided by the vapor density of the first gas, right? Okay, and for this equation again there are some other forms. What are the other forms? That is you know that what is the rate? The rate is equal to R is equal to volume that is diffused divided by the time it is travel, time taken to travel, right? R is equal to V by T. Okay, so here you assume that there are two gases with the same value, the V, and here is also V is same. Okay, but the time taken spread from one place to the another place. Okay, here you have spread and it has to go from here to here. Okay, so first gas ki enta time తీసుకుందంటే you assume that T1, and that for this gas this is the first gas and this is the second gas. So ఈ first gas ki enta time తీసుకుంది అనుకుంటాను, that it will take the T1, right? And for the second gas it has taken T2 time. Okay, for the same distance. Okay, so now what is the relation is that if the T1 and T2 are the times of diffusion for identical volume of two different gases, if it is a A and this is a B. Okay, so what is that volume? For the two different gases the volume is same, but the time traveled is different. Okay, and now what is the relation? Right, very simple. For the first gas, what is the R1? The first gas is equal, what is that? V is the volume and the time taken is a T1. Okay, and similarly for the second gas, what is that? The R2 is equal V by T2, right? So now when you take the ratio, that is R1 by R2 is equal, again V will become cancelled, right? Okay, so that is R1 by R2 is equal to V by T1 divided by V by T2. So V and V will come cancelled. So finally what you can get? That you can get only the T2 by T1. Okay, so that means there is a one condition. Okay, condition lopata rendu gases unnai, two different gases. There are two different gases with the same value, but their rate of time of diffusions are different. Okay, and at that conditions the rate ratio, the R1 by R2 is equal to T2 by T1. Okay, and again come to the second case. Enti anante, here the volumes are different. There are two gases A and B. The volumes are different. Now the volume here it is a V1 and here it is a V2, but the time traveled is same, that is T. Rendu gases kuda same time lopata travel avutayi anamata. Okay, here the volume is different but the time is same. Then what is the R1? The R1 is equal to V1 by T. This is the R1. Then what about the R2? The R2 is equal to V2 by T. Okay, so again you take the R1 by R2, what you can get? You can get V1 by V2. Okay, so these are the some relations is very important in the point of problems calculations. Okay, now we can see few applications that you read these applications. Nothing is important here, applications, but of course it is important, but nothing is to explain. Okay, so read these applications. Okay, and next we can go to some problems. So you see here there is a problem on the Graham's law of diffusion. Okay, what is that problem? Is that you see 360 centimeter cube of methane gas diffused through a porous membrane in 15 minutes. Okay, so that means there is some membrane here, and through this membrane the methane gas. Okay, so what is the volume of this? The 360 centimeter cube. So this much of volume of methane gas passed through this membrane, through this porous membrane in a time of 15 minutes. Okay, similarly under the similar conditions there is another gas, that is 120 centimeters cube of another gas diffused in 10 minutes. Then find the molar mass of that gas. Okay, so here we don't know that other gas. What is the other gas? But that gas diffused in a 10 minutes with the volume 120 centimeter cube. Okay, so that means here you have two different gases. One is a methane and another one is a unknown gas. Okay, so let us see here. So first is the methane gas, and what is the volume? That is 360 centimeter cube, and the time it is diffused is 15 minutes. Okay, right? Okay, and then the unknown gas, you take the unknown gas. What is the volume here they have taken? It is a 120 centimeter cube, and the time it is diffused is a 10 minutes. Okay, so what you have to find? The molar mass, M2. M is nothing but molar mass, how much. Okay, so for the first gas, what is the molar mass? Methane, you know that methane, carbon is a 12, hydrogen is a 1, so 4 hydrogens are there, so that 12 plus 4 into 1, this is 16 grams per mole, 16 gram per mole. Okay, so that is 16 gram per mole. Okay, right. So now what you have to do, you have to find out the M2. But how can you find out the M2? Is that there is a relation, there is a relation. What is that relation? That is, according to the Gram's law of diffusion, R1 by R2 is equal square root of M2 by M1, M2 by M1. Okay, so what you have to find out? You have to find out the M2. Okay, you have a M1 value, but do you know the R1, R2? Yes, R1, R2 we know we can calculate. How? The R1 is nothing but the volume that is diffused in a time. Okay, so how much volume he has taken? 360 centimeter cube, and that is traveled in a 15 minutes. So that is 360 divided by 15, that is 24 centimeter cube per minute. So that is the R1. Come to the R2 again. This volume 120 centimeter cube of unknown gas diffused in a 10 minutes. So that means the R2 is equal to V2 by T2, that is 120 by 10. This is 12 centimeter cube per minute inverse. Okay, so that means you know the R1, R2 as well as the M1. So you need to find out the M2 value. Okay, so that you substitute. 24 divided by 12 is equal square root of M2 by 16. So this 16 is the molar mass of the methane, molar mass of methane. Okay, so that is M2 is equal to 4 into 16, that is 64 grams per mole inverse. Okay, like this you can calculate the unknown gases molar masses by using the Graham's law of diffusion. Okay, so now you see the one more problem, that is the carbon dioxide and another gas X have their rates of diffusion directly. Rates of diffusion ichadu chudandi, that is 0.290 cc per second, cc ante centimeter cube per second, and 0.271 cc per second respectively. Then find the vapor density of the gas X if the vapor density of the carbon dioxide is 22. Okay, so vapor density formula enti manaki very simple, rate of diffusion, that is, what is that formula? That is R1 by R2 is equal square root of VD2 divided by VD1. Okay, so that means vapor density of the second gas divided by the vapor density of the first gas. So let us see here, rate of diffusion of carbon dioxide divided by rate of diffusion of the gas X is equal to this is R1, so that vapor density of the one will come down. Okay, that is square root of vapor density of gas X divided by the vapor density of the carbon dioxide. Very simple, substitute the values and find out the vapor density of the X, that is 25.19. Okay, so this is the Graham's law of diffusion, and in the next class we are going to see the Dalton's law of partial pressure, Dalton's law of partial pressures. Okay.